This is Unit 36, refrigeration applied to air conditioning. On this first slide, refrigeration process applied to comfort cooling is classified as high temperature refrigeration system. Typically our evaporator coils are at 40 degrees Fahrenheit. We use the same four components as in other refrigeration systems, which consist of the compressor, the condenser, the metering device, and the evaporator. Absorbs heat indoors and puts it outside. Structural heat gain, very important subject here. Heat leaks into a structure by conduction, infiltration, and radiation. Summer solar load on a structure is higher on the east and the west sides of the buildings. I know this very, very well. Attic ventilation can help relieve the solar load on the ceiling. It's accomplished with powered or natural draft ventilation systems. I might add, on new construction in California, we now utilize a ply-score plywood, which has a foil face, which is facing towards the attic side. And what is great about this, it creates a reflective barrier when applied to the roof structure, so that the solar rays are repelled away from that plywood sheathing with this aluminum foil face backing, and it reflects back up to the roof. So on the new houses, such as the one I live in, as an example, I've noticed a huge benefit as far as keeping the house easier to keep cool in the summertime versus a 50-year-old structure that did not have this sort of thing. Structural heat gain, conduction, and infiltration. Heat enters through the walls, closed windows, closed doors by conduction, and by infiltration through cracks around doors and windows. Infiltrating air has different characteristics. Humidity, depending on location, that must be taken into account. And one of the things on older houses, some people will elect to hire a company or a person to take and do what they call a heat loss, heat gain analysis of the structure. And they'll use thermal imaging guns, they will use visual inspection, construction techniques, composite construction of any room additions, and things like a ceiling on top of a ceiling, as an example, or penetrations through the ceiling, like for electrical boxes which are not properly sealed, show up. And you'd be very surprised how much things like that will infiltrate and cause your heat load to rise inside a residence or a commercial building. Here we have a structure. This is a house here. Notice that the outside temperature is 95, probably like today. Here we have a powered attic vent fan. It's 100 degrees Fahrenheit. The summer sun heats the attic, and the attic heats the ceiling. Now, the idea behind the attic fan, of course, is to take and pull some of this hot air out. There is another way to do it. They use what they call a whole house attic fan, basically where it's in the hallway. You turn this thing on in the morning and you force all the hot air out of the structure through the attic and out through the louvers in the side of the building. That's another process. But what I said earlier really applies here. On the new construction, or if you're going to do a re-roof, one of the things I recommend doing now is tearing off the wood sub-base on the structure and install this plywood with the foil face. By installing that with the foil face on the attic side, you repel the heat back outside and never penetrates inside. And I can tell you right now, it makes your attic probably a minimum 20 degrees cooler than with the old type of construction. Now over here, we have a situation where we're not using forced air in the form of an attic vent fan. The hot air basically is going to collect inside the attic. Hopefully you have insulation, and then basically you got vents. It's going to take and push the hot air out through the vents. The problem with this is the heat becomes entrapped, vents get clogged up, and a lot of times there's not enough vents in the inside of the attic structure to relieve all the heat out. So I think in some cases, and I'm thinking older construction, I'm not concerned about new construction. Older construction, this is more apparent and needs to be addressed. It's not enough just to put great insulation between the ceiling and the attic. That's definitely helps as long as you take in as long as you fix all the boxes, the cracks, and all the heat leakage that takes place through the structure. Certainly helps, but in the grand scheme of things, I really think you have to pay attention to that heat that is trapped up in the attic in a hot day. And as an air conditioning expert, I can't tell you how many hot attics I've had to endure through the years, and I'm just very thankful that I'm still okay at this point in my life in working in these hot attics. So basically, this figure basically says the ventilated attic keeps the solar heat from the ceiling of the house, which is a true statement if it's done correctly. Structural heat gain difference locations. Okay, outside here on the left we have 90 degrees Fahrenheit. Temperature difference is 15 degrees. So basically, if we look at the inside of the structure, which is 15, the outside is 90, so we have a 15-degree difference between out and in. So this is in Augusta, Georgia. But I might also add they're not taking into effect the relative humidity, which is probably 65–70%. Now you come over here, Phoenix, Arizona. The structure here in Phoenix, it's very hot there, and today I think it's like 109, 110. So basically today on this illustration they show 105 degrees outside ambient temperature, 80 degrees indoor, so we got a 25-degree ambient. On the newer houses that they're building in the Phoenix metro area, basically they're doing a better job of insulating the new houses and getting this temperature difference. Typically on the super hot days, I mean this still applies, but I'm just saying that I would as long as the windows are closed, the doors are closed, you should be able to maintain 75 degrees even if it's 115 degrees outside. The difference between Augusta, Georgia and Phoenix, Arizona is the relative humidity. That plays a huge role in the comfort. Phoenix is dry climate. Augusta, Georgia is a damp, humid environment. Evaporative cooling. I've talked a lot about this in the past and I'll talk about it again. It is used primarily in climates with low humidity. SoCal, coastal regions are not a low humid area. Typically our humidity here in this part between the ocean and I would say all the way to Riverside, San Bernardino is typically 40% relative humidity. Well, Larry, it feels hot and dry. Yes, during Santa Ana wind events, it does. Normally, if you were to take do a humidity check outside, you would find the humidity, especially on a day like today, as an example. I see thunderheads developing to the east of me in Riverside as we speak. And I would venture to say probably later this afternoon, the relative humidity might reach 45–50%. Obviously, if it goes to 80–90, that means it's raining. Simple as that. But getting back to evaporative cooling, low humidity is a key there. If you have a dry climate such as Phoenix, Arizona, such as Indio, California, or Palm Springs, it would work, okay? It utilizes fiber mounted on a frame with water running over the fiber as a cooling media. Fresh air is drawn through the fiber and cooled by evaporation. Must have an outlet for air that has entered to leave the structure or it will be pressurized. 3 common configurations: the drip type swamp cooler where the water just drips down the pads, the spray or Singer type swamp cooler, and the rotary type swamp cooler. If it's a rotary swamp cooler, it's going to be a large wheel that has like copper or brass screen pockets to allow airflow. through the screen, and there'll be a tank in the shape of a half moon, which is full of water. And what will happen is this: the tank will be full of water, and this rotary evaporator, this wheel will turn on a call for cooling, and it'll take the water into the rotary screen, and then of course air is pushed across that, and of course the end result is you have a area that is cooled by a swamp cooler. The only problem with swamp coolers, or evaporative cooling as we call it right here, is that the air tends to be loaded up with moisture. Okay, too much moisture can be very destructive, just as well as too little moisture can be. So that being said, one of the issues that I have here is basically you're basically dumping a lot of moisture into the air, and in some cases this creates problems with mold growth and some other issues. Now, next sentence says an outlet must be an outlet for air that is entered to leave the structure or will pressurize. So if you take and fill up a house utilizing a swamp cooler, you basically have to have an open window or some way to push this hot, dry air out of the structure. So that's the disadvantage there. 3 common configurations, like we said again, the swamp cooler is going to be the spray slinger type swamp cooler, or the rotary swamp cooler. Here's an example of a swamp cooler in this picture here. Notice this is one that it mounts in a window. Typically you'll have chains that'll support the case here, or you'll build up a stand right under here. You'll hook up a potable water supply here. Water will fill the sump here. Here we'll have a pump, which is going to take and water that's collecting in the tray here in the pan, and is going to be pressurized and brought up to a distributor, and the water will basically drip onto the pads here. Okay, swamp coolers must be maintained. Swamp cooler pads need to be changed out a minimum of once every season. This system has to be cleaned up. One of the problems with swamp coolers is the water quality. If the water quality is really poor, which it usually is, basically you're going to put minerals on the panels, and eventually you're going to create corrosion. You're going to create all kinds of issues. The way that you can minimize corrosion buildup is on this pump discharge line. You would put a T, and you would put a 1/4 inch line, like a dripper line, whatever like that, off of this T, off this discharge line, and take it down to your plants down below. By doing that, you're going to take what they call the TDS, the total dissolved solids, and remove that out of the water stream and put it in the flower bed, and basically double the life expectancy of the swamper as you see it. Package type and split type air conditioning systems. Air conditioning, comfort cooling, or high temperature refrigeration systems operate with the same 4 components. Package air conditioning systems are self-contained, all components in one cabinet with air ducted to and from the unit. A split system air conditioner consists of a condenser outside, removed from the evaporator through the use of piping by refrigerant lines, and ductless mini splits are of the same design. But the ductless mini splits are better in one respect, because you don't have no ductwork issues, because basically each room is served by a mini split. If you size those things correctly, you can basically deflect and send the air where it's most needed. They're super efficient, super inexpensive to operate. They do a fantastic job. Evaporator transfers the heat from the air to the refrigerant. Absorbing sensible heat lowers the air temperature. Now, sensible heat is the heat that we can feel. That's the heat we can measure. This is not the same thing as what they call hidden heat or enthalpy. Now, latent heat. So basically here, absorbing latent heat removes the moisture by changing the water vapor into condensate, which is drained. So in air conditioning, you are absorbing latent heat, which you cannot measure, and basically it will remove moisture by changing the water vapor into a condensate form, which is drained outside the structure or into your sewer system. Typical room conditions: 75 degrees wet bulb, 50% relative humidity, 62.5 degrees wet bulb temperature. These are your design conditions for comfort cooling in a house or an office. Evaporative coil operates at about 40 degrees Fahrenheit. Okay, so on a refrigeration, air conditioning application, all the evaporator coils are designed for 40 degrees, period. I don't care what it is. I don't care if it's a mini split. I don't care if it's a split system. I don't care if it's a package. The magic number is that coil should be able to discharge 40 degree air out of that coil. Well, Larry, I'm not getting 40 degrees out of that unit on my house. Well, that's true, because remember, it's traveling through ductwork, it's traveling through walls, areas where heat is being absorbed into that temperature at the evaporator. We're talking about at the evaporator coil. Once it leaves the evaporator coil, the magic rule is basically add 10 degrees. So typically we would expect to see about 50 degrees on the supply outlets on a structure. Okay, here's another important piece of information. Air leaving the coil at about 55 degrees. Remember I said 50? I basically shoot for 50, but typically 55 is normal. Dry bulb and about 95% relative humidity. Humidity is high because the air has been cooled. The relative humidity will fall when mixed. Okay? When the climate is humid, such as Augusta, Georgia, the coil temperature may lower to remove more humidity. Coil temperature is controlled by airflow across the coil. Airflow affects the coil temperature. Well, how about the more air, the better? A caution note. If you have too much air across the evaporator coil, what happens to your ability to take and remove humidity? Okay, so basically the coil temperatures will have to be lower temperature in order to remove more humidity. But if you have too much air blowing across it, you're going to upset the balance where you're not going to be comfortable. Okay, too much air across the evaporator coil is just as bad as too little air. If we have too little air, we're going to have frosting, we're going to have freeze up problems. If we have too much air, basically we're not going to remove all the heat that is coming into the evaporator coil from the structure. Evaporator coil configurations. The evaporator is a refrigeration coil made up of aluminum or copper with aluminum fins to increase heat exchange surface. I might add a footnote on the new evaporator coils. For most systems I'm installing currently, they're all aluminum. The manufacturers have pretty much given up on copper and aluminum fins because of the expense and corrosion and dissimilar metal problems. So on your new coils today, and I'm talking about 2021 now, basically we are utilizing all aluminum coils. And for the most part, it appears to be working. I think the jury's still out on longevity, leak issues, things like that. But we do not have the issues with dissimilar metals taking place. Common evaporator coil types: A coil, slant coil, and an H coil. Coils may be operated in parallel to avoid large pressure drops, and they may each use multiple circuits within a distributor. Microchannel, a flat plate and fin technology coil designs that resemble the automotive radiators. Microchannel is in widespread use with some manufacturers today. It works for the most part because it increases the heat surface contact, but I will tell you this: if you ever get a leak on a microchannel coil, good luck trying to fix it. It's a real problem because the metal's thin. There are issues you have to deal with. Here's an example of an A coil. It's funny, I'm looking at this because I worked on an evaporator coil in West Covina this morning on a service call. And I'll tell you what, it had a TXV, which you see right over here. And what was rather interesting, there was leaks. There's a Teflon O-ring on this side, and then there was a Teflon O-ring on this side where this TXV was located. And then you had these this distributor which has capillary tubes. These capillary tubes were actually laying in this pan. Well, one of them, that would have been number 6, because this thing had basically 6. It had 6 portions of the coil. And what I mean by that, basically 6 circuits. Instead of one circuit where the refrigerant flows through in and out, this thing was divided into 6 circuits. And the number 6 circuit had the copper laying in the moisture-laden pan, which you see here in this illustration. And basically what happened was the corrosion from the water condensate from the air being cooled put a hole in the capillary tubing. I was very fortunate. I was able to take and repair that capillary tubing with silver phosphate, utilizing a lower flame temperature without burning through and cutting the capillary tube. So, and if you'll notice, this particular coil is an older style utilizing copper, and then of course aluminum for the fins. And the other thing is, and you can't really see it here, but this coil has the appearance of being very, very dirty. One of the things that I pay very strict attention to is evaporator coils that get full of dirt. And the reason why they get full of dirt is if you look below, they have a cheap filter on this illustration. The cheap filter is basically no filter at all. Basically lets 90% of the dirt go through. That dirt's going to end up underneath this evaporator coil. It will decrease the heat, resist the heat removal capability of that evaporator coil. It'll reduce the airflow across the coil, and eventually, if you let it go long enough, it'll block the coil so badly with dirt that you're only going to get 30% of airflow through the system, and everybody thinks that the ductwork is bad, when in the actual truth of the matter is the underside of this evaporator coil is loaded up with dirt. It does happen on a frequent basis, and a lot of people don't know about anything about filters. All right, design conditions. You need to be familiar with the local design practices. Choose equipment utilizing climate condition charts. Single speed, non-inverted control equipment performs most efficiently when running at full load. Many designers compromise between selecting 1 to 5% conditions by choosing a 2.5% conditions or by utilizing variable speed capacity system. So what am I saying? We are utilizing today constant torque / ECM type motor technology. The idea is we ramp up, ramp down based on the loads, and by doing that, we can get a better handle on heat removal. Mini splits have done this for years, and they work fabulous. They're great. I have no issues with them. Very seldom do I ever have to replace parts on a mini split because they're so well designed. As far as the motor, the ECM motor versus the constant run type motor, these motors ramp up, ramp down based on the actual need at that given time. The compressor types include the reciprocating, rotary, scroll, centrifugal, and screw. Utilize the same designs that are similarly used, there are similar types used in commercial refrigeration. A vapor pump that pumps heat-laden vapor from low-pressure evaporator side of the system to the high-pressure condenser side by compressing the vapor. Increases the temperature and the pressure of the vapor. Compressor speeds. RPM plays a key point as far as circulating refrigerant vapor. Older, small, and medium-sized compressors, single-speed pumps, and turn at about a standard motor speed between 3450 or 1750 RPM, depending on the type of motor used on the hermetic compressor. The newer single-speed compressors operate at faster speed and they're more efficient refrigerants utilized with this process. Most systems today utilize variable refrigerant flow technology to vary the speed of the compressor motor in order to control and adjust capacity. So what are we saying? We no longer have a fixed one speed takes care of the air conditioning. Basically, now we ramp up, ramp down based on the actual load conditions measured at the thermostat. And by doing that, we can figure out if we need more air or less air based on the information such as the dry bulb, the wet bulb, and the latent heat that is measured in the space. Reciprocating compressor utilized in residential light commercial air conditioning, mainly cooled by suction gas and air passing over the shell of the compressor. Usually the fully hermetic suction gas cooled type. There are positive displacement compressors utilizing R22, R410A, or R407C refrigerants. Cooling the compressor and the motor. On a hermetic compressor, compressors are cooled by refrigerant. Lack of cooling results in damage and breakdown of the compressor oil. Hermetic compressors are suction gas cooled. That's why we don't send liquid back to the hermetic motors. We want to have low temperature, low pressure vapor. And we send that back. It will basically take and cool those windings outside the compressor and cause the compressor to operate very efficiently. Rotary compressors are cooled with discharge gas that leaves the compressor. Newer compressor motors can run at higher temperatures. Technicians should determine that the temperature is correct on the discharge line, but not over 225 degrees. It's been shown if you have a temperature of over 225 degrees on the discharge line, you will cause the oil inside that compressor to break down. Well, Larry, how do you measure that? It's very simple. You just take a thermometer or a sensor and attach it to the discharge line. We do not want to see that temperature above 225 degrees. If it's much higher, you need to find out why and take corrective action so that you don't take and destroy that compressor because the oil is overheating at a temperature above 225 degrees Fahrenheit. Rotary compressor, small, light, and sometimes cooled with compressor discharge gas. It's more efficient than a reciprocating compressor. Discharges all refrigerant that enters it. There's two basic types: stationary vane rotary compressor, rotary vane rotary compressor. Scroll compressor utilizes two spirals. One is stationary and the other one is orbiting. The two scrolls form a multiple individual pocket where the refrigerant is trapped. The pockets get smaller as the refrigerant passes through the compressor. Several compression stages occur simultaneously, and they're very highly efficient. High performance depends on good axial and radial sealing. A condenser, component that rejects the heat from the air conditioning system to the outside. In this case, most equipment is air-cooled and rejects heat to the air. Coils are made of copper or aluminum and have aluminum fins to take and increase the heat exchange surface area. New coil designs are utilized in some units that make them lighter and more efficient. Now here's an interesting concept right here. Side air discharge condensing units. These would be like your narrow profile units where you don't have much cement, where you can have a standard, as an example, 3-ton condensing unit which measures 36 by 36. If you have a situation like, say, in a condominium where the sidewalk area is only 30 inches or less, now you got a problem. You still need to have an air conditioner location. They make these what they call horizontal discharge, and this is another name for side air discharge. Discharges the air out the side of the unit. So the fan's mounted on the side instead of on the top. The fan and motor are located under a top panel. Noise generated from inside the cabinets discharge into the airstream. Heat from the condenser coil can be hot enough to kill plants if it blows on. So if you're going to put one of these type of units on a structure, make sure the customer doesn't have very sensitive plants, because when that air conditioner is running, it will blow hot air onto those plants and kill them for the most part. Top-Air-Discharge condensing units. The most popular configuration for condensing units in residential equipment. Hot air and noise is discharged from the top. Motor is on top and should be protected with a rain shield, unless it's a shaft down application. Bearings mounted in vertical position need a thrust surface. So basically, if it's mounted in a vertical position, there should be enough play in the motor to for what they call axial thrust. In other words, movement from one end bell to the other end bell. In this unit 36.30 shows discharge air from the top. The fan usually is on the top. Now, one of the things I hate about trees, although they provide shading and make the air temperature a little bit cooler around that air conditioning unit, trees shed leaves. These have to be cleaned out of these condensers on a periodic annual basis. As an example, if you don't do this, the leaves and debris will pile up. They'll actually block the coil. It will affect the efficiency of the unit and the operation of the unit during a really hot day. Condenser coil design. Vertical condenser coils may be clogged with grass and dirt. Coils must be cleaned to operate efficiently. Bottom rows of coils may be used for subcooling. Pardon me. Lowers the condensed refrigerant temperature below the condensing temperature, adds to the efficiency of the system. High efficiency condensers. HVACR industry and the federal government demand higher efficiency. One of the best methods is to lower the head pressure. But in order to lower the head pressure, typically they make these units large. Larger coils, greater surface area, lower head pressure, lower compressor ratio, and bottom line, less power consumed. The downside of these large, high efficiency condensers is the ability, they take up a lot of space. In some cases, they're a little bit hard to clean depending on the coil design. Getting them, like I said, into a space sometimes requires a crane because the physical size will not allow passing through a 36-inch wide gate, as an example. I've seen some units manufactured by Rheem Company. These units actually, residential units now, utilizing communicating thermostats, inverter technology. Interestingly enough, these units are super efficient, but they have one big drawback: the physical size of the outdoor unit. They're typically about anywhere from 5 to 6 feet high and 36 by 36, which presents challenges as trying to move that equipment into position, or in some cases working on it. Condenser cabinet design. Cabinets are usually located outside, so they need waterproofing. Aluminum is lightweight, but is susceptible to rust in salty environments. Well, I find that hard to believe. Rust in salty environments. I've never seen an aluminum coil rust. I've seen corrosion. Small equipment is assembled with self-tapping screws made of weather-resistant sheet metals. Fasten screws tightly when installing equipment in the field to prevent rattling. That's a very good point, because typically especially on scroll compressors, they do produce a little bit of vibration. I worked on a unit in Rancho Cucamonga yesterday, relocated it, and then started the thing up, and I noticed that the thing was rattling, and we had a few areas of the cabinet where the screws were loose. We tightened those up. Some cases we had to actually put like a rubber cushion between the outside grill and the fan top in order to kill the vibration so it wouldn't transmit across the frame. Expansion devices are controlling the flow of refrigerant into the evaporator. Most common types are fixed bore and TXV. Electronic expansion valves, EEVs, are utilized on almost all ductless split systems. TXVs are more efficient. Evaporator reaches peak performance faster. Refrigerant pressures in the TXV system typically do not equalize during the off cycle, requiring compressor utilize high starting torque motors. Airside components consist of the indoor blower as well as the supply and return ducting. Airflow is typically designed about 400 CFM per ton in an average climate. In California, under the Title 24, we design our systems for 350 CFM. And basically, when you have a HERS rater coming out to commission a new system, they will check this. And if you do not have that 350 CFM per ton on the return side, you basically fail the installation, and you have to make corrections to the ductwork or to the air handler or air speed, whatever, in order to get that CFM up. So in the coastal areas, we design for 350 CFM and 450 CFM per ton in the desert area. So in this case, out here towards Riverside, Indio, Palm Springs, the air conditioning equipment is usually designed for 450 CFM per ton because we're dealing with a lot more heat here than we are in the coastal areas. Air leaving the evaporator coil at 55 degrees and returns back at about 75. So that's where the 20-degree split comes into play. Ductwork for the air handler running through unconditioned space must be well insulated. That's a no doubt. I've seen many houses where the ductwork literally falls apart after 15-20 years, and because of heat issues, because of the plastic deteriorating on flexible duct, and typically this means you have to replace all the ductwork. The newer ductwork that's being sold and installed in housing and commercial has like a silver reflective coating on this polymer plastic, which tends to make the ducting last over a longer period of time. Cool air distributes better from supply registers located high in the room. Remember, heat rises, so you want to knock out the heat up towards the ceiling. If you do that, then the rest of the room will be fine. So your air registers are typically in the ceiling or high sidewalls, as an example. And I might add that the type of register the air is delivered through plays a very key important role if you're going to keep that place cool or not. Stamped grills don't cut it, in my opinion, as far as air conditioning or, for that matter, heating. Installation procedure. Package systems, whole air conditioners are in one cabinet. An example would be a window unit or window shaker, as I like to talk about that. Equipment located outside the structure so the service can be done outside. Complete factory assemble and charged with the short, efficient refrigerant lines. To install, mount and on a firm foundation and connect the ductwork and with electrical service. It looks easier than it is. It's a lot of work, guys, especially when you're putting in a mini split system or a split system. There's just lots of things that have to be done. Locate the condensing unit and the air handler as close together as possible. Install interconnecting piping, the cool gas suction line and the liquid line. The cool gas suction line should be well insulated. Under Title 24 in California, it has to be a minimum 3/4 inch thick. Take care when handling the equipment. Watch out for insects, sharp objects, weak ceilings, and lines carrying refrigerant. People have been known to fall from ceilings or get in trouble because they weren't paying attention to their surrounding environment where this equipment is located.